Hello again, my chemistry people, and welcome back to your final installment of your redox reaction chapters. Yesterday we talked about, well, I guess maybe not yesterday, but the day before yesterday, we talked about voltaic cells and how they take chemical energy and turn it into electrical energy by like taking advantage of these, like the different properties of these two different metals, right? You put like one metal over here, you put one metal over there, and like whoever's higher on table J loses the electrons, whoever's lower on table J gains the electrons, and that's what kind of pushes the electrons through the wire. Really, the force is like the difference in electronegativity. So the metal with the greater electronegativity is actually pulling on those electrons. It forces them through the wire. And when we have the salt bridge there to allow the balance of charge, the electrons can flow. Electricity happens. Wow, we're in the 21st century. However, that's not where it ends. That's only one kind of electrochemical cell. That's the most common one, the one that we're most familiar with, and one that is like the most amazing to us. However, we are going to take a look at what happens when we force a redox reaction to happen. So remember, a voltaic cell happens spontaneously. The electrons are going from a higher metal to a lower metal on table J. We can, however, like I mentioned before, force electrons to go in a direction that they wouldn't go naturally, or they wouldn't go spontaneously. It happens in nature like all the time, just we're going to be more control of it this time. And that is called, wait for it, electrolytic cells. Right there you are. Right there. Okay, so electrolytic cells. Here is the deal with electrolytic cells. Oh, let me get my colors going. There we go. It is a non-spontaneous redox reaction. In other words, it's like the electrons are probably going up. Right? They are climbing on table J. They are not falling down, and it is forced to occur by an outside power source. This is the most important part about an electrolytic cell, and the one thing that really separates the electrolytic from the voltaic. There's an outside power source. In other words, you have to put energy into it to make it happen. And basically what happens with an electrolytic cell is that the spontaneous redox reaction of a voltaic cell can be reversed and the system can be recharged. This is the most common use for your electrolytic cell, at least what you see in your everyday life. This is like literally what happens. So here we go. We're going to also talk about electrolytic cells, I mean, that's it, right? So we're going to talk about a couple of different uses, like how we use these electrolytic cells in our everyday lives. And this is the first one. So if you remember, electrolytic cell, first of all. See, here's your outside. There's your outside power source right there. You understand what I'm saying? That's a battery. And what we had before with our voltaic cell is we had a whole bunch of zinc in here. We had a whole bunch of copper in here. But if you remember, all the copper got blopped onto this electrode and got reduced into copper metal. Right? And so this solution had no more copper ions. Over here on the other side, all of the zinc metal had come out into solution and created tons and tons of zinc 2+. And if you remember, what kills a battery is if this electrode is dissolved or if you use up all the ions. It looks like in this case we just happen to use up all the ions, and inside our salt bridge we had sodium ions, we had chlorine ions. The chlorine migrated into here because this is where all the positive ions are building up, and all the sodium ions migrated into here because this is where all the electrons were going. And remember, it did that to balance out charge, and then it goes and goes and then it stops because look, it looks like we used up all of our copper. So if you want to recharge it, what happens, dog, if you attach this thing to a battery, right? A battery is basically an electron pump. So what it does is it literally forces electrons to go in a certain direction, and it's labeled, right? So this guy right here, this is the negative side of the battery, this is the positive side of the battery, and what that means is the electrons go shooting out the negative side. And electrons, cable management, the electrons are like forced into the positive end. They are forced by what? This thing, a battery. It's basically an electron pump. That's what happens when you plug something into your socket like your wall socket, the power grid is literally an electron pump, and it pumps electrons through all of our electric devices. Then they work, yay. But this one, if you notice, we are forcing the electrons to go this way, backwards, from copper to zinc. And if you look on table J, copper is below, zinc is above. So this is non-spontaneous. And what happens here, if you want to follow the electrons, is we attach it to this battery. This battery rips 2 electrons off. Does you see that little piece of copper right down there? Yeah, see that little guy? It rips 2 electrons. And then this thing, that little piece of copper, turns into a copper ion. The electrons flow through the battery pump. They are pumped into here, where you have 2 little electrons, and guess what happens over here? Same thing, only opposite. Now that you have 2 electrons, a zinc is attracted to those 2 electrons, bloop, turns into a piece of zinc metal, and the ion is like replaced by the metal. And this keeps happening. The battery keeps pumping, electrons keep going, copper keeps coming out of solution, or I'm sorry, into solution. The copper metal loses their electrons. All the electrons flow through the battery. They come back in here. All of these zinc ions gather up their electrons until, you've either used up all the zinc ions or you've dissolved the copper, and then you're done. That's it. That's how you recharge a battery. Now, all batteries can't be recharged because the force of this going through, right, sometimes requires so much energy that it just breaks down the structure of the battery and it can't really be recharged. That's why some batteries are not rechargeable and some batteries are. It really depends on the metal. It depends on what kind of solution they're using, what they're using for a salt bridge, all that kind of stuff. So that's why not all batteries can be replaced. But that is how we recharge a battery. You just take an outside power source to force the electrons to go in the non-spontaneous direction, and you do exactly like you did before, right? So over here, the zinc 2 plus is gaining 2 electrons and is turning into elemental zinc. And over here, the copper metal loses 2 electrons and becomes a copper ion. Are you guys picking up what I'm putting down? Yeah, you see how it's the exact opposite? This is reduction, and this is oxidation. This is the anode. Because remember, anox, this is the cathode. Because red cat, right? This is still an electrode. That's still an electrode. This is still a salt bridge, this is still a half cell. That's still a half cell. That's still a salt bridge. Get it? Just the major difference is that things have gotten flip-flopped from when they were a voltaic cell because the electrons are going in the non-spontaneous direction. How do you know? Outside power source. Dig? I hope you dig. Hope you're picking up what I'm putting down because we're moving on. Here we go. The use of electrical energy to force a chemical reaction to occur is called electrolysis. That's the name for basically what we're doing here, right? That's a good vocab word, electrolysis. And it's what's happening inside an electrolytic cell. So this is one of the things we use it to change, to recharge batteries. We also use it to make elements like sodium metal. Dude, you will never find that in nature. So how is it that I have a jar of sodium metal back in the chemical storage room if you will never find it in nature? Well, by an electrolytic cell, right? We take sodium chloride and we perform electrolysis on it. We basically force the redox reaction to happen backwards, where it goes from, let's write the 2 half reactions. We start with sodium with a +1 charge, and it turns into sodium metal with 0 charge. That means we must be adding an electron. Right? Yeah. And over here, we start with chlorine with a -1 charge, and we're going to end with chlorine with a 0 charge. And that means that the chlorine is spitting out or giving up that 1 electron. Does that make sense? So who gets oxidized? Who gets reduced? There you go. Leo says Gur, losing electrons Leo. Oh, this is oxidation. This is reduction. Now remember, it's always the reactants that get oxidized or reduced. It's never the products. So I mean, that's another major use for electrolysis. Is it's how we produce metals. For example, aluminum used to be more valuable than gold because it is unbelievably reactive, and we can never find it in elemental form. And it's really, really useful because it's everywhere right now, right? Until literally some dude in college was learning this exact thing, and he was like, dude, why don't I just do electrolysis on all the aluminum ions that are like one of the most abundant elements? Dude made bank until they made so much aluminum, it's like one of the most common metals around. Not in nature. Naturally, aluminum is always in a compound because it's so intensely reactive. But now, in the modern 21st century, electrolysis has made aluminum one of the most common metals floating around. How? Like that. You dig? Nice. So what are some other things we do with electrolysis? Electroplating. That sounds like a very big, like, vocab word. I'm going to go like vocab word. Yay. So what is electroplating? Basically cover one metal with a very, very, very thin layer of another metal. I'm sure you all are aware of this. If you buy like kind of cheap jewelry, like a silver ring, you put it on, think, oh, that's all beautiful. And then like you put the ring on and off 2 or 3 times, and then the inside looks not so much like silver, and then your finger turns green or funny colors. It's because it was a ring made out of cheap metal, but electroplated with like very, very, very thin layer of silver with a process called electroplating. Here's how this works. Oh, I have a diagram and everything. Let me check that out. Nice. I like the spin. I should have had a spork. It's better than that one. Anyway, here we go. So here's how it works. First things first, man. You see this? That's gold. That is gold right there. Because it is an outside power source. That's how we know that it is an electrolytic cell. So here's what do. The battery is an electron pump, and it's going to pump electrons into here. And that means that this spoon is going to gain a whole bunch of like negative charge. Now, where do these electrons come from? It comes from this silver bar. This is how silver plating works. We have a big hunk of silver. We have a solution with silver ions. And we have a thing. It's going to be a spoon. We have a silver plated spoon. It's literally how they make a lot of silver cutlery. So the battery pumps electrons. Electrons leave this hunk of silver, right? So that means a little bit of silver stops being silver metal and turns into the silver ion, right? And that electron goes zinging up here, gets pumped through the battery, lands in the spoon, and that silver ion comes over here and is attracted to the negative charges, and then absorbs one electron and turns into a hunk of metal. The battery takes yet another electron, pumps it through the battery into here, and this little silver ion that came into solution gobbles up another electron and turns into a little lump of silver. And you do that, and then another electron goes up, another ion goes on. Another electron goes up, another ion goes on. Another electron goes up, another ion goes on. And you can see how this will very soon be coated in a very thin layer of silver. And when you're all done, you take it out, rinse it off, and bam, you have a like silver-looking spoon. Silver spoon. Oh, wow, that's a show from the 80s. I don't know if any of you have seen it. 2 silver spoons. All right, here we go. Sorry, I just aged myself. So, yeah, the key here is that this is a non-spontaneous reaction. If you put a spoon made out of, I don't know, aluminum, silver, or not silver, tin, like whatever, iron, it's not going to automatically like plate itself, but with an outside power source it does. And here we have what's happening at this electrode, right? And here is what we have happening at this electrode. Because remember, electrodes are where oxidation or reduction occur. So this is losing an electron, Leo. This is oxidation, right? So if this is oxidation, Leo says Gur, red cat, and ox, this is going to be the anode. Awesome. This is gaining electrons. Leo says Gur, reduction. Leo says Gur, red cat, Leo says GR, red cat anode. Okay, so this is my cathode. Does this make sense? I hope so, because this is where reduction is happening. All these ions are gaining electrons and turning into silver metal. Super sweet. Where does the oxidation occur? Silver bar. Where does the reduction occur? Where does the gaining of electrons occur? Spoon. Red cathode. What acts at... Oh, I just did that. I answered both of them. Where? The silver bar. Cathode. Spoon. Silver bar. Cathode. You guys get what I'm saying. I answered both of them. It's just weird how it's like tripping out on me. It's not sticking. All right. Last thing I want to talk to you about is the electrolysis of water. This is a relatively important thing, mostly because it's water, and everything about water is like really, really important. So here's how we split water into its elemental forms. It's also, not for nothing, one of the ways that we produce oxygen for people to breathe who might, say, have some kind of respiratory illness or disease or problem or emphysema or some other weird thing that's affecting the way people breathe. These are like little mobile units that can produce oxygen. You can actually buy these over the counter or for like home use and whatnot. But here's how it works. First, we have an outside power source. Do you see how that is automatically an electrolytic cell? For our electrodes, it doesn't matter what the metal is in this case. So let's just call it copper because that's the most common metal used in wires and stuff. So because we're not acting on the metals here, this is all about the outside power source. And I want you to just look for a quick minute. All right, this is high quality H2O. High quality H2O. And these, believe it or not, this can also happen inside the same container. So you don't even need necessarily to have the salt bridge. This can all happen inside the same container. So I want you to take a look. First at this equation, 2 water molecules, right? You produce 2 moles of hydrogen and 1 mole of oxygen. So twice as much hydrogen as you do oxygen, right? So to do our half reactions, we've got hydrogen as +1. It's going to turn into hydrogen with a 0. Oh man, that's so bad. Let me just hold on for a second. That was just so bad. I gotta do it again. Hydrogen with a +1 turns into hydrogen with a 0 charge. So we got to add 1 electron here. Oxygen with a 2- turns into oxygen with a 0, and there are 2 electrons that pop out. Do you see how you need like 2 hydrogens for every oxygen? Because if each oxygen spits out 2 electrons, we need 2 of the hydrogens to absorb both of those electrons, right? Now, just by looking at this, right, you can tell which side is going to be the hydrogen gas, what side is going to be the oxygen gas. So, before we go any further, Leo says GR, gaining electrons, reduction. Losing electrons. Okay, so oxidation, which must be this one, right? Because we have half as many bubbles as we do over here. This is producing twice as much gas as this one, because you have to. Because look, remember the whole 2 electron thing. So this must be where the oxygen is happening. This has to be O2, which makes this oxidation cathode. Wait, oxidation. Good catch. Anode. 5 pillars. Man, I made a mistake. But I caught myself by saying, Leo says GR, red cat and ox, electrons roll downhill. Red cat and ox. So if this is oxidation, it's got to be an anode. If this is reduction, red cat. Red cat and ox. Bam. That was easy. Stu making mistakes. It's weird. It never happens. Ever. I never make a terrible. Hey man, don't judge. Don't judge. I know you really know it. Where are the 2? Oh, what are the 2 half reactions? Well, right here's one half reaction. Right there's the other half reaction. which is the cathode, which is the anode. We just did that. What gas forms at the cathode? Well, it's got to be hydrogen because hydrogen ion has to be reduced. What gas forms at the anode? O2. Because the oxygen with a -2 is oxidized. You guys understand what I'm saying here? Because the oxygen is oxidized, that has to be the anode, right? Because that's where oxidation happens. And how do we know that oxygen is being oxidized? I wrote out the half reaction, right? And same thing with the hydrogen. It has to be the cathode, because that's where reduction happens. Reduction happens at the cathode. And how do I know that hydrogen is being reduced? Again, I wrote out the half reaction. I can see this going from +1 to 0. Charge is being reduced, dropping, lowering, whatever you want to call it. You guys picking up what I'm putting down? Certainly hope so, because that's it for today. What I do have for you is the homework number 5, electrolytic cells. Get in it, get on it.